Ladies and gentlemen, we're starting, please.
Okay, good morning, everyone. Just a little organizational thing. It would be good if you guys could take your cups and your plates you brought in here out with you, at least at the end of the day. Also, you might have seen in your throw bags, you also have got these called keep cups. So they are like this. So they are basically recyclable coffee. Reusable coffee mug. So instead of using some of the cups there, you could also use that, so that helps create less rubbish and makes it easier for us at the end of the day. And otherwise, the bus for tonight is leaving at 5:30 from right out here. So everyone will go on it, I assume. So there shouldn't be any difficulties there.
Okay, thank you, Walter. By the way, you may have seen my brother here yesterday, the guy at the time. And by the way, I'm not going to chair every session. And I'm not Tara Murphy either. Tara couldn't make it early this morning, so I'll take over from that. Okay, so on with the show. And this morning I'm delighted to welcome my mate and colleague, George Strakowski from Caltech, who is really the brains who started off this series of Astroinformatics conferences, for which this is the fourth that is. Yeah. So, over to you, George.
Well, thank you, Ray. Well, good morning. Thank you all for actually getting up. Unlike those others. I've been tasked to put this whole thing in a little broader context, but I would also like to focus on some of the outstanding challenges that are still with us, and in order to open the discussion. So the whole fourth paradigm, so it's a phrase due to Jim Gray, the late great computer scientist who helped us a lot. And the idea is that science began with experiment with Galileo and so on, and quickly we got analytical theory. Those two served us very well for a few centuries. And mid-20th century, we got something new. We got computers who essentially do a whole lot of partial differential equations really fast, which is what was called the third paradigm, in addition to the previous two. And then, as the role of computing changed in the 80s and 90s, that it's no longer just about crunching numbers, but it's about processing information, Jim Gray coined this phrase of the fourth paradigm, the data-driven science. And the question naturally arises, is this really something new or just more data? And I'll address that in a little bit. There are several important trends that affect all of science today that are driven largely by the exponential growth of data volume, but not just that. And all sciences are going through this, somewhat different starting points. The data are doubling every year and a half or so, according to Moore's law, because the devices that produce the data are described by the Moore's law. And if you think about what that means, it's actually quite remarkable. It means that a year and a half from now, we'll have as much new data as we had in all of the past history. And that keeps going, and derivative of an exponential is also an exponential, so the data rates keep growing. But more important thing in my mind is not so much growth of data volume, but data complexity. They were measuring more things. And so, for example, in a sky survey, for each source, you may have 300 numbers measured. And that complexity is what really gives us a lot of, both a lot of potential for interesting data mining, but also a lot of challenges. So we transitioned from data poverty to data glut. And most people don't understand the importance of this because most people, not you young folks, but old guys like me, grew up in the era of data poverty, and you clutch to the data because that's the basis of science, and ownership of data is it. But when you have too much data, data are not blessings, data are curse. And it's the ownership of expertise and creativity that matters, and you can have as much data as you can possibly wish. So that's an interesting shift, good shift in the focus. Another thing is that the data are no longer static things. Data evolve. Even the same data set keeps changing as you recalibrate it, add new stuff, and so on. So data evolve themselves, which is part of the issue of reproducibility and so on. And because there is so much of it, and it comes in so fast, you're driven to real-time processing and analysis, otherwise you'll never catch up. Moreover, a lot of interesting phenomena happen in time domain, and therefore you must analyze them in real time. Also, there are distributed resources, different archives in different places, and so on, and this will grow rise of virtual observatories and so on. Now, an even more profound transformation, I think, happens in theory. And again, this is, I think, paradigm shift that most people didn't quite grasp. Namely that now theory, in addition to old good analytical theory, is done through numerical simulations, and not because people are too dumb or lazy to derive formulae, but because there is no other way. That we have theory that's intrinsically non-analytical, that is produced through numerical experiments, and that's what they are, and its output is not formulae, but data, theoretical data. And so now the theory also becomes data-driven science, which of course those theoretical data need to be matched with real observed data. There are all interesting challenges right there. So this is a very interesting thing, that we have an intrinsically non-analytical theory which is now data-driven. So together, this is all working very well, that we have information technology that's giving us this new enablement in science, but then science, us, should be helping develop new tools to digest all this, because as the subtitle of this conference implies, it's not about data, it's about knowledge from data. And all sciences have the same problem, and in fact, not just sciences. All aspects of modern society are having these same problems, we may as well be avant-garde. So since the beginning of the whole virtual observatory movement and so on, we have good, mutually beneficial collaborations with applied computer scientists, and Jim Gray stands as an outstanding example, but we can keep, we must keep running. And so they started transition from this subsistence regime of observe few objects at a time, clutch to your data, publish a paper, to the industrial enterprise driven largely by sky surveys, which in the 1990s pushed us into a terascale regime, and now we're getting into a pettascale regime. So 15 years later, that's 10 cycles of Moore's law, factor of 1,000, and that's exactly on schedule. And all this is driven by the progress in information technology, VLSI electronics. Moore's law does the data doubles every year and a half, gets better, there's more of it, and the real action now is on the back end. What do you do with the data? So the computer is the new telescope. The telescope and the instrument are just the front end that provide the data. And you observe sky, which is your archive, through your software instrument, which is some kind of analysis algorithm. Now, as technology develops, it opens up new portions of the observable parameter space. And I would argue that throughout history of astronomy, our progress was driven by technology opening up new pieces of parameter space. A good analysis of this was done by Martin Harvit, who looked at things in a very general way and put a whole bunch of diagrams like these. This shows time resolution of a given wavelength regime, and areas of different shading correspond to different times. So first we could observe variable stars on scales of, I don't know, hours, days, whatever, invisible light, and then expanded over different wavelengths and so on. First time somebody could observe in radio and millisecond scales, new phenomenon potentially discovered, the pulsars. First, gamma ray sky opened up, discovered gamma ray burst, and so on. So observable parameter space, flux, coverage, depth, everything. It's even sky surveys, right? And so if you can plot them somehow in this parameter space of observables, you can see what we covered and what we didn't, and you can design your new missions or surveys accordingly. Now, that's as far as observations go. Then you measure sources. And for them, you have a different parameter space of measured properties, magnitudes, colors, whatever, right? And sometimes those measured properties correspond to physical properties, like colors tell you something about spectral energy distribution, and this is how we found almost all quasars that we know. But then if you somehow get to the physical property, masses, whatever, sizes, then you have physical parameter space, and that's where the interesting things really happen. So this is an example of parameter space of hot stellar systems. The axes are radius, velocity dispersion, surface brightness, and you can see that they're really separate nicely in different families, and there are interesting correlations involved and so on. Another familiar example of this will be two-dimensional parameter space of color and magnitude, or luminosity and temperature, and this is how we understand stars. So by putting in theory and also some other data such as distances to stars, you translate from observable parameter space to the physical parameter space. This is where you can compare with models and so on and so forth. So that is a very general framework within which you can look at systematic exploration of the universe in observable parameter spaces. Brian kind of semi-derogatively said, oh, it's a blind searches. It's not blind searches. Nobody's doing blind searches. Open your eyes wide. It's a systematic exploration of the observable parameter space, because every time you analyze the data, you put a filter in it of some sort. If you're looking for supernovae and optimize your survey to find supernovae, you'll find supernovae, but you'll miss a whole bunch of other stuff. And so if you systematically check for all things that reasonably could be there, chances are you'll find some interesting things. And so here is a shop-worn diagram of how the modern scientific process goes, from gathering a lot of data, or data farming, archives, so on. We know how to do this. Then comes the interesting part, knowledge discovery, and there are where we have most of the current challenges, how to do this in an effective way. I'll talk about this later. And in the end is finally the prize, a new understanding of the universe. This is where the real role of scientists comes in. But even there, technology is important. So from the get-go, I started thinking, what's new here? Why is that is not the same thing with more data? And there are two reasons. The first one is that for the first time in history, we cannot look at all of our data. Most data we take will never be seen by a human eye. And so that means we need certain type of technologies to make sure we're doing the right thing. The more interesting thing is that almost surely, inside this amazingly rich informational pile, there are structures, correlations, regularities that cannot be directly comprehended or noticed by a human mind, because there are too many dimensions involved or hidden in some way and so on. And this is where you really need computer science help. This is where the interesting new stuff comes in. And of course, everybody else is right. So a dozen years ago, Virtual Observatory came along with similar organizations in other fields, and basically they all responded to the data glut. They all had semi-properties. They're a new kind of institution, inherently distributed. They were not based on institutions, but in a discipline. Virtual Observatory does not exist at Caltech or Harvard or any place like that. It exists in astronomy, right? There are many different institutions that correspond to it, from bricks and mortar to clicks and bits, right? And you have to adjust to the exponentially growing technology, cross the boundaries, walk with computer scientists, and so on. Well, that worked fine for a while. And so what we've accomplished so far is essentially we built a global data grid of astronomy. It squeaks here and there, but it exists. A lot of boring but important stuff was done in laying down this infrastructure. What hasn't happened is equally good development of knowledge discovery tools. And this is, of course, where science comes from, and this is what people pay attention to, and this is ultimately the reason why we had such a low take-up of these concepts in our community. So this is where I think Astroinformatics has become. Okay, here's a little provocative question. Has VO outlived its usefulness? Yes and no. We do need that infrastructure and hope we'll have it forever and get it better. But as it has been done so far, it has not fulfilled a crucial role of aiding discovery through more than just data infrastructure. And this is why we have to do something else. This is why we came up with new meaningless buzzword of Astroinformatics as what comes next beyond VO, a means to involve broader community in the discovery process as contributors and as users of these tools. Because if you think about it, most discoveries don't happen in data centers. Most discoveries happen in PI-led groups, university-based, observatory-based, tackle some scientific problem, discover new things, sometimes make real useful software tools as well.
George,
Yeah.
do I phone truck?
Yeah.
I cannot let that statement go past. Still no significant VO-enabled discoveries. Can you name a Python-enabled discovery? You get my point. That I totally agree with you.
Yeah.
We need to move
Yeah,
away
yeah.
from
Let me clarify
VO
this.
tools are just tools. That's all they are.
All of these tools contribute in some way. So, you know, sure, you look at ADS and you look at NET and so on, and that contributed to your discovery.
Yeah.
And those are part of this underlying tissue. But it will be very hard to point out to papers that if we didn't have virtual observatory tools and services, this would have never happened.
Well, in terms of NED and everything else.
Yeah, maybe. Okay. But potential thing.
So every student uses TopCat.
Right. Virtual observatory itself is a swindle, right? I mean, there is no such thing. As we always said, it's like Holy Roman Empire, right? It's neither holy nor Roman nor an empire. Anyway, so now we see a rise of science informatics, Tony talked about, and we have Astroinformatics, Bio and Geo and whatever. And there are fields that cross into the applied computer science statistics. And so that indeed is, you know, what this is all about, right? Okay, so we have stuff to do, and there are two kinds of challenges, technological scientific challenges, and there are sociological ones. And they've been with us for the last 15 years and still the first one is, the reason why you can make discoveries in these masses of data are twofold. First, the more data you got, higher the chances you find something interesting, right? Like rare objects, if it's 1 in a billion, a few billion objects. And more importantly, in data fusion, as you start combining things, usually things happen on these interfaces and edges, like optical IDs of, say, radio sources, voila, quasars, right? That kind of thing. But data mining of such data sets is not an easy task. Numbers of data vectors, data volume, are not a problem. Good algorithms go as n log n. You just buy yourself more computers. The real problem is dimensionality of the problem. If you're dealing with 5-dimensional data set, you can buy off-the-shelf software, do data mining for 2 times. If you have 1,000-dimensional data set, you are out of luck. These things don't scale very well. They can keep supercomputers busy forever, especially anything Bayesian, which is supposedly the right way to do statistics. And so this is where we need to work more with computer scientists, because this is how you actually get to make use of data. You have 3D, sure. What about if 3,000 dimensions? Then you're really, really out of luck. This is where we need applied computer science to help us. And the visualization of these hyperdimensional spaces is an unsolved problem in computer science. Most of the work in visualization is on better 3D for the obvious reasons, right? So this, I think, is the single hardest problem we have, because there are surely, the universe does not limit itself to 1-dimensional and 2-dimensional correlations. There are probably 50-dimensional correlations in 1,000-dimensional parameter spaces, and because 50 is a lot less than 1,000, there is some interesting physics going on there, right? But also, a lot of data mining algorithms make assumptions about data, like is everything Gaussian, right? We're like, nothing is ever Gaussian. And so, if you apply wrong technique on a given data distribution, you're going to get results. Garbage in, garbage out. It applies on methods as well as the data, right? And so visualization, data mining go hand in hand, and in the end, understanding comes from that, right? So this, I think, is really the single most important challenge. And more broadly, if you think about it, right? I mean, what's the science for? Science takes the big, messy phenomenology of the world and finds simpler rules by which things behave. Laws of physics. Newton's law of gravity, moon and the apple do the same thing, right? Rockets as well, right? Well, maybe we're out of all the simple stuff. Maybe Newton's laws of physics are much more complicated than something you can write easily on a piece of paper. But nevertheless, they reduce complex, messy phenomenology into rules and regulations. And science's job is to find it. So this is, I think, going to be one of the more promising areas in the future. The collaborative human-computer discovery, where we use machine intelligence to help us guide through otherwise incomprehensible mess of data. In the end, scientist has to make a discovery and understand what's going on, but the path to that may be aided by machine intelligence. And this has been envisioned for a long, long time. It's only that now we're starting to have technology that might enable us to do this. Right? We've done a little experiment. I hope Matthew Graham will talk about this later, where we used off-the-shelf program for machine discovery called Eurega. And basically, you feed it a library of mathematical functions, and it looks at your data and comes up with a functional analytical description of these data using this library of functions without knowing anything about physics behind. Then you look at formulae and try to understand why this. So first we had it rediscover known things like HR diagram, main sequence, fundamental plane, and it does that. The program doesn't know anything about galaxies, but it finds the functional form that actually describes something that we already know is interesting. Then we used it to classify objects, because you could take function, multiply by Heaviside function, and then you have left or right, different kinds of things. And it does that really well on different kinds of variable stars. The program doesn't know about stars or pulsations or anything. It just looks at the data and says, well, here is your functional description that can tell you what's going on. So this is just the first step. A more important thing is happening in the, what I call visual context, time domain now that we're looking at. Turns out when you find something with magnet, you know nothing about it other than where it is and how bright it is. Everything else you know about it is from the past archives, different wavelengths, different times, and from what's around it in the picture. The carbon-based brain in your head has no difficulty of immediately telling you something is an artifact, or well, this galaxy probably has to do something with that random source, and encoding this in a pipeline is almost impossible, because there is an infinite number of possibilities. If something that went bang tonight has actually done this before, that cannot be a supernova, right? Because star can only explode once, and so on. So finding a way to describe and encode contextual information in all these senses, and as well as domain expertise, is, I think, going to be a really interesting. So we've been trying to do a project like this called Astrocollation for some time, and the idea is that to have intelligent crowdsourcing to annotate images or detections and turn them into semantic descriptors and algorithms and so on. So there are several uses of machine intelligence, and for astronomy, how our carbon brains can be aided by silicon brains, and they're kind of obvious. So let's get back to fourth paradigm. My answer to is this something really new? Yes, and that comes from three different things. One is first that you can do data mining, which you just couldn't visually recognize. You can do data fusion, which reveals knowledge present in the data that's not identifiable in any of the data sets separately. And it can use machine intelligence to help you go through all this. So these three things, in my mind, is what makes the fourth paradigm science. One other thing that I'd like to introduce is the open data philosophy. Just like we had open source philosophy that served people very well, I think now that we have so much data, we should go into a complete open data philosophy. Make your data publicly available right away to anybody. Properly documented, of course, right? And so we've done this with Catalina Real-Time Transient Survey. We publish transient events we find immediately to the whole world electronically. Anybody can follow up. People scoop us things. We also made public an archive of 500 million light curves containing a couple of 100 billion data points in them, which is an unprecedented data set. You can mine it. Who knows what's in there? Simple, quick, fast, with millions of variables, several tens of thousands of pulsating variables, 20,000 new RLRE, we map galactic halo, time tracer. There is gold to be had there. And this is not served out of Caltech, but we'll move to a Ukraine, India short. An issue that I would like to talk about, but I don't have time, is how do we change scientific publishing? We keep talking about this, how to really make use of information technology to broaden the concept of what's publishable. Every intellectual product should be publishable and given credit in some form or other, but should be done online. Abandon the data-free media. And I think we have to abandon traditional form like paper printed commercial journals. Say you want to have a journal about astronomy and computing. The worst possible thing you can do is go with commercial publisher and have a paper journal that costs arm and a leg for library to subscribe. We also know that peer review system's broken, but necessary. Why not use new online tools to do it? We can exchange information with other fields, like with biology. And we started poking at this. There is a little essay we wrote, our golden astrogenomics, which is a completely bogus word. It's just to attract attention. How we can use virtual observatory infrastructure to help genomics organize their own data. And this, in first month, was the most downloaded paper in this journal. What about training people with new skills? We've known that already. Along with myself, been trying to develop something we call post-textbook in practical astroinformatics, an interactive learning environment that will be modular, innovative. Talk to us, we'll tell you all about it. We use online tools, online resources to do this as much as possible. You can all contribute to it too. So we need to train this new generation, you guys, how to do the science. Few random thoughts before I end. Computational science is not computer science. And I find that card-carrying computer scientists tend to be a real obstacle. Right? You want those who really understand their applications. Having computer scientists in charge of this kind of stuff is like having mathematicians in charge of every scientific project. Right? This is different. It's not about data, it's about knowledge extraction. Data are cheap. Computer science brings us now together, bridges the gaps. Just like mathematics did, universal language of science, now you have computational skills, but a new universal language of science that can connect this. So here's my summary of the key challenges that I just talked about, career paths properly, published, trained, and so on. So here are my conclusions, really, that this is part of a much broader thing. That science is being transformed completely in the 21st century by the information technology that generates exponential or super exponential flood of data, and that science changes scientific methods. And we all share same problems. Does it make sense to try to collaborate between different disciplines and try to solve them together? Moreover, computers are cheap, and because commercial industry pays for them, really, for the development, you can get much more bang for the buck if you build astroinformatics engine than to build a telescope. Telescopes are expensive because they're one-off pieces of equipment. They now go into billions of dollars or whatever. Computers are a lot cheaper. And originally, virtual observatory framework was our way to try to answer these challenges. It did some things, it didn't do other things. And astroinformatics, I think, is our new playground in which we do this. And so I'll just put up some words of wisdom and take your questions.
I like that. Right, questions for George? Oh, well, let me kick off with one. More a thought, a random thought while you talk. You talk about three spaces. There's the space of theories, there's the space of data, and there's the space of the physical space, I think you called it, where you draw luminosity functions and things like that. And it's in that physical space that our brains work best. That's where we visualize stuff. But if you're going to test a hypothesis against the data, that's maybe not the best place. So the trouble about going from data to luminosity function is that you've always got problems really hard to...
Oh, I'm not minimizing any of that. I mean, you have the same old problems, only much more.
Yeah, so what I'm suggesting is that there's if you want to test a hypothesis that's maybe not best tested in the physical space within the data space.
Right.
So it's the same thing. You don't take, same way as you don't take the data to the user, you take the user to the data.
Absolutely. No. It was just like a 5-minute description. Yes. I mean, we tell students you do not project data into theory, you project theory into the data.
Right.
Right?
Okay.
Yep. That stays with us.
This is a fantastic paper by Fire-Runner. Synthesize just.
Okay,
Watch two models.
I'll get the reference. I'll tweet it when I get the reference. Sorry, George doesn't like tweets. You're showing your age, George. Right, but up there.
So you've suggested to address the broader astronomical community with this new data influx. Do you think citizen science could really help with these new challenges? Do you think they'll be able to keep up with the amount of data, something like Galaxy Zoo, but
No.
expanded? No, not enough.
Citizen science has been grossly oversold. It's a wonderful outreach device. There is very, very little genuine new science that you can do with citizen scientists. There is a reason why people go to school for 20 years. Okay? Among other things, knowing what they're looking at and what they're doing. Now, having said that, there are possible intelligent ways of deploying citizen scientists to assist with tasks which we still cannot offload to the machines. And on the other hand, human attention doesn't scale. And right now, you can do quick little demo projects, Galaxy Zoo or whatever zoo, but that's not going to scale to the next generation of observatories. This is why we're trying so hard to capture human pattern recognition skills and informed domain expertise, turn them into algorithms that then can scale. You only want human attention at the very end for the most interesting, most important things. So yes, I think citizen science can help us on this intermediate stage of trying to teach the machines why the humans make a decision, this is X versus Y. And some data collection in some fields. But I would say overall, you're not going to have millions of people who don't know what the heck they're looking at and make fundamental new discoveries. I think there's only one thing that Galaxy Zoo has discovered, and that's Honey's object. Everything else was previously known. And doable by machines.
Greenpeace is another example, I think.
But
What about Zwicky?
in a way, Hennes Vorwerf is a red herring. That's not what citizen science is really. I mean, it's a lovely example, but that's. I think the problem with that is that people think, oh yes, that's what citizen science is about. It's lots of people looking at things, looking at something alike. Whereas in fact, I think there's been enormous amounts of science come out of citizen science, but it's not the one big spectacular discovery. It's through people doing classifications and cross-IDs. And I would say more because Julie Banter is going to give a talk about this later in the week. But I think maybe we tend to think of citizen science to be something that's not quite. We may not be that far apart, but the big spectacular things are really rare. There's another tool I think is incredibly powerful.
I have a methodological concern. I've been spending my life trying to teach machines to mimic human brain behavior to make discoveries. So I find citizen science is just a contradiction. It's a way to teach a bunch of humans to produce human life.
For you, those who can't hear Pepe, he said that he spent his lifetime trying to teach machines to think like humans.
Yes, exactly.
And citizen science doing the opposite. I think that's the point, that good citizen science doesn't. Citizen science takes the pattern recognition abilities of the human brain and integrates them into the algorithm.
I think I agree. The intentions are all correct. What I'm challenging is that the outcome is actually the matters.
So let's postpone this discussion until Julie's talking.
So I was very glad to stress the importance of open data, and so yesterday we heard about URIs and DOIs for data. What organization can do that for us? If if I go and do a fantastic survey and open up all my data, I don't get any kudos for the science. But if I get kudos for the data, I'm more than happy.
That's the key thing that Virtual Observatory has been doing, developing interoperability standards and protocols and so on. One of the very first things that first Virtual Observatory did was to put how to file, how to expose your data in a standardized fashion to the rest of the world Virtual Observatory. So yes, I think between various and sundry Virtual Observatory bodies, we've been developing precisely that. So it's just go look it up on the website.
But is that proper citable? Can somebody cite that as a paper?
No,
As they would a paper?
no, good things. You're asking, are there formats? Yes. How do you get credit for publishing data? Now, that is an interesting thing. Right now, what we do is old crutch of publishing a bogus paper that says, here is long.
Sorry, I was just going to add to the DOI comment. DOIs are generic, they're not specific to any domain. The Australian National Data Service provides a service to get the DOI data to any domain in the country, and that's internationally linked in the data site. And a DOI, all it is a permanent, unchanging reference to a website. When you click on a DOI, it takes you to the website, but it's a unique URI that will never change. So that already exists.
But the problem is ARC grant proposals don't have space where you put in how many hits you get on the DOI.
But that's changing.
I hope it does, yeah. Alex?
Yeah, so I was recently at the Royal Society meeting, and there were very obvious stresses there between the machine learning people and the statistics people. So would you care to elaborate?
No, would you? There are such things everywhere. I just don't understand that sociology good enough to make a good comment, but it's silly, I think. In my mind, a lot of data mining is algorithmic applications of the statistics, but not all.
No, so where I was actually getting with this is that, for example, there is a Netflix challenge, which was one of the more interesting examples of machine learning, applied machine learning. And it was a hodgepodge of about 1,000 different algorithms put together, shoved into the kitchen sink, and then a heuristic applied on top of it, which gave the best fit. And so it was not exactly a statistical approach.
I think we're all learning how to do this right.
I don't remember who said that data mining with machine learning is just statistical practical recognition with incomplete information.
Any more questions? Okay, thank you very much, George. Okay, so now we have Andy Green, who's going to tell us how to work together on the software.
So just to pick up on a point that came up in the last conversation, when thinking about software engineers and computer scientists, a really good analogy I've gotten recently is a pure mathematician is to an applied mathematician, as a computer scientist is to a software engineer. That's a good thing to keep in the back of your mind. Somehow I've started at the end of my talk, and I'll start my talk. Let's try to begin. So this is a little bit of a shift gears. This is a much more practical talk about how we embraced some of the software engineering challenges in modern astronomy inside the SAMI survey. So I'll just dive in. So the old paradigm is a single astronomer sits in front of their computer and they hack out a bunch of software and then they write the paper and they publish it and get all the credit. And this is exactly what I did with my PhD. I had a sample of about 70 galaxies, roughly 50,000 spectra. I actually only needed a very small piece of that spectra, which meant that I could, over the 4 years of my PhD, write about 2,500 lines of code. producing this 2,500 lines number was complicated because I wasn't very well organized. So enter the Sammy Galaxy survey, which I won't describe in too much detail because I think some other talks are going to pick up on it more. The things to take away is, although it's smaller sample size in terms of number of galaxies than SLUM, the final data product will have about 8 million spectra in it. And they're spatially resolved data cubes, so the spectra are correlated spatially with themselves within each galaxy. The data isn't particularly large. There's only going to be a few terabytes of data in the end. And there are about 80 people working in this project. So we had a lot of software to write to deal with these 8 million spectra. So I'll just explain some of the ideas and discussions that we had and the conclusions we came to, and hope that you guys can learn from that when you have to do something for yourself. So the first thing, and I really don't know how we managed to bully the team into using Python, but we managed to bully the team into using Python. A couple of the reasons for that: it's freely available, it's open source. I, for one, was terrified of having to deal with yet another nightmare of making an IDL license work on my laptop. It can be easy to read. You can always write bad code in any language, but Python does tend to lend itself towards writing easier to read code, because I think I've found that to be true. It's reasonably widely adopted, not just in the astronomy community. An awful lot of people in here put their hands up when we asked yesterday how many people use it, but it's being picked up from a lot of completely commercial applications as well. And so I think it's here to stay, at least for a little while, hopefully longer than some of the shorter-lived ones. People don't realize this. Python is actually a benevolent dictatorship. There is one single person who says this is how it will be. What will happen when we no longer have that one single person? Manage a bunch of people working on software. So this is just a snapshot out of our versioning system. And each of these little dots is actually a piece of code that's checked into the repository. Each of the vertical lines is a separate branch of the code that's being independently developed by a different user. There's about a dozen parallel channels going on here, and it might look like absolute mayhem, but in reality, having a piece of software, a current versioning system that can actually look after this for you, made it incredibly easy to get on in this way. We weren't constantly sending emails with attached files code. These are just a couple of the different systems that do this. Subversion, which some would argue is maybe a bit old hat, although I think it still has its places. And Mercurial and Get, we actually chose Mercurial on the grounds that it's actually a single executable. It's also written in Python, but I don't think there's any strong case to be made for any of these. They're all good. You just need to pick one and figure out how to use it. Unfortunately, they have a little bit of a steep learning curve up front if you've never used something like this before. It probably took me a week of writing code and fiddling with it to really figure it out and get to where I could use it. I didn't think in the end that was that big an overhead for the reality of being able to develop in parallel effectively. You'll also want a centralized server, especially GitHub or Get and Mercurial don't in themselves have a centralized server. They're inherently decentralized, but the practicalities of working in astronomy mean you probably want to go to one of these websites, sign up for a free account, and you can host your code there for free. If you're worried, you can even keep it internal until you're ready to release it in an open source method. And also, this was a big help for dealing with the mayhem of all of these concurrent versions of the code flying around in some kind of GUI interface. And this is the one that I use and have encouraged the team to use, although I've discovered recently it's no longer developed. And it's just showing you what you can get. So I've highlighted two different versions of the code, a couple of versions apart. It shows me that only one file in the code base has changed between those two versions. And then there's also, conveniently, it keeps track of the descriptions of what each person did when they made a change. So in this particular version, I was fixing a bug in the orientation of our data cubes. James over here fixed a bug in another bit of code. So you actually have documented what changes you've made in kind of human readable form alongside the changes that you've made in the code. And you can even look at those changes line by line and go, okay, you convince yourself how things have changed. The other thing that I was actually very surprised was how easy it was to merge different versions of the code. As long as you're kind of sensible about different people working on reasonably separate things, it's almost trivial to merge in the changes. So when one person goes off and works on something for 3 months and comes back, it's often 5 minutes to merge that back together. Occasionally you get mayhem and it's much worse. We've all had our horror stories, but it was much less difficult than I expected. Another thing that we've only just started to think more about is how we keep track of small changes or large changes in the code base and also in our thinking. So for instance, we had a lot of trouble figuring out exactly how our flux propagation went through the physical algorithm we're using. So in the end, we've had to think about, well, writing longer, more detailed descriptions. Many papers that are not really intended to be papers so much as just a very verbose description. This is what I did, so someone else can read it, convince themselves of what you're doing, and then they can paraphrase that into the paper. They can paraphrase that into what's written in the code. Another thing that we decided on, which I think was an excellent idea, is having a system of maintainers. So each different bit of the code is maintained by a different person, and these maintainers really work as gatekeepers into the code database. And the really good example that I can find of this is actually the Linux kernel. So Linus Torvalds has, the master copy of the Linux kernel sitting on his laptop, and it's an open source community. Anybody can contribute code, but obviously Linus doesn't really want a random person to suddenly check in a new branch or new version that then breaks the whole kernel and it all falls in heap. So he actually does what are called pulls. So he has a group of trusted maintainers that look after particular aspects of this kernel, and he pulls changes from each of their separate copies of the code base. He says, okay, this person's made a change to the device driver. I trust that they've looked after that change, they know it's accurate, etc. He pulls it in. If he was really careful or really concerned, he might look carefully at a particular change set before he actually applied it to his master copy. And then each of these trusted maintainers actually acts as the kind of gatekeeper from the larger community. So, this developer might be known to him, and he might have a quick look at the change he's proposed and say, oh yeah, that looks quite reasonable. Whereas, another developer maybe has never heard of it before, so you look at it, maybe the developer says, oh, this is a really good idea, looks at it a little more carefully, and actually, oh yes, this actually is a good idea, it's well described, because we're looking, so he pulls it in. So in the model we've adopted in SAMI, this is kind of our master copy of the code. We have a master branch, effectively, and then these maintainers look after different aspects of the code and basically act as gatekeepers to test just writing the code. I mean, what's the difference? I mean, if I'm going to test the code, then I have to write the code to test the code, don't I? No. It's much more simple. Think about, kind of various sanity checks that you can do on that code to make sure that, it's giving you something reasonable out. The same kind of sanity checks that you're going to do when you're actually developing the code, and you run it, and you look at output, and you say, well, that doesn't make sense. They're all nans. The results of my flux calibration are all nans. Well, that's a very simple test that you can write. It's probably 2 lines of code that says, well, is the output actually an array of real numbers? Check. Okay. You can run all of these things. So it can be very small. Another example is if you're doing some kind of spatial transformation of your data, if I have a galaxy that has a bright spot on the east end, does it have a bright spot on the east end in my output? In other words, do I have the orientation of my spatial transform correct? These kinds of tests seem kind of trivial when you think about them, but the fact that you can build many of them up makes them exceptionally powerful. So when you then have a very complicated piece of code and you make a change, or maybe a largest change because maybe you realize that there's a better way to do something, it can be very complicated to figure out how, whether actually the change has been valid or not. So sometimes we've gotten quite far into, I'm happy to admit that I've not written enough of these things, and so I made a change to the code that for James that re-reduced half the data before he discovered that the output was correct. So I had to go back and fix it. So basically, unit test, you give it a bunch of random or predetermined inputs where you have a pretty good idea of what the output should look like, and you check that the output matches the expectations. And actually, I mean, this last point I think is very important. You're going to write a paper at the end that says this is what the result is. You want some confidence that result is correct. We're lucky in astronomy that we don't have to go to court to argue that our results are correct, but there are fields, actually in the same building that I work in, where people do have to go to court and say, yes, I'm confident that these results are correct, and my results may send somebody to prison for 10 years. So this kind of confidence is highly useful. So how did we come out in the end? Or how have we come out so far? Because we're nowhere near the end. So I'll only talk about the data production pipeline itself. There's also a lot of other code being written within Xamarin. We've had our repository for about 8 months. The history of the code actually goes even further back than that. There's been about 400 commits to that repository in the 8 months. And I was actually quite surprised. There's about 10,000 lines of code that have been written in those 8 months. And actually, this is something that Miriam mentioned or asked me about, is the comment to code ratio. So this is for every 10 lines of code, we've written about 4 lines of comments, basically making our code readable so someone else can come and look at it. And we've had this happen, usually within the team, where one person writes the code, someone else then comes and reads it and tries to convince themselves that that's what they think. That was my last slide, my last point. But I think so far that kind of suggests that we have been quite successful with the approach that we've taken. Thank you.
Thanks, Eddie. Questions? Jessica.
Have you, as a team, decided what code to write, what your next priorities are, or how do you go about that decision process?
That's a really good question. So far there's certain things they're obviously needed. So we've gone down those paths first. And then we've also, but so far it's been largely organic. People say, well, this is something I need for my research, and then that's what they write. And that's actually where a lot of our focus has come from. I mean, we could say, the kind of two approaches you can take. You can say, well, this is what I want, 10 years from now. What do I have to write to get there? And you can sink endless postdocs' careers into the first year of writing code and not publishing any results. So far we've tried to take the approach more, well, getting the flux calibration correct is important for someone's science, so that person is then taking the lead on trying to get the code necessary.
This is more a comment. I was pleased to see you had a slide there on testing, because it's something that most astronomers as coders do not do. And when I have spoken to software engineers, they've fallen on the floor in amazement that we don't test our code. And obviously, bigger projects are probably better at doing this sort of thing. But really, the difficulty for in a lot of cases is we don't actually know what the correct output is to test it. And that's quite a foreign concept to software engineers as well. In cases like this where you're doing an obvious test, do I have real numbers, do I have, that's fine. But when you're asking if you don't get the flux correct, or what is the correct flux? What's my test case? Sure.
Well,
but it's not always done.
Yeah, and it's interesting. I mean, I might almost argue that it's not the case that astronomers don't do any testing, but I think so far, often the level of the problem the astronomer is trying to solve is such that they can do a mental test. We all plot.
Well, they don't test in the same way a software engineer would test with boundary conditions and testing every single if statement.
Yeah. And honestly, whether an astronomer needs to do that or not, I don't know. But you can go and do the kind of visual test when you're writing the code. Well, is this the output I expect, or roughly the output I expect? And that's a form of testing. I think the problem lies in when you start to write, a large piece of code that's greater than the sum of its parts. Is that you can't do that level of testing every time you make a change.
Yeah, I agree.
with that, you can. And you should set up automated processes. And even if that testing takes a week, then when you do major changes or when 2 bits of major code have to come together for something, you have to do that testing. We stop testing when we get the result we expect, right? And then 6 months later, you find a bug in your code, and that result you expect no longer comes out. And it turns out you've got 2 bugs in your code that are cancelling out. I mean, I'm sure everybody in this room has had that experience.
Oh yeah, I mean,
Insanely common, so that has to be a standard that you use. And we don't as astronomers do it. We're insanely bad.
Okay.
There was one comment more or less the same like there are astronomers and astronomers. Even Dice here knows very well what is behind Concurrent writing software. One of the best examples was Chips, which was made in the 80s, so very but there were strict rules for documentation, there were internal checking the quality of the documentation, there was testing, this was a very good astronomers were in the right environment, it's not always good software writing practice. Even individuals write code which is impossible to use. It's impossible to do messaging, even this is not what people do. Testing is a good advantage. Metadata.
Two questions. One, what proportion of your project's time is spent on testing compared with development? And is your testing done by people who don't do the development?
those are both good questions. In terms of fraction of time, I'm not sure I have a quick answer. Partially because we haven't, you know, I mean, like I said, some of us have put down some writing tests for our bits of code, some of us haven't, some of us haven't spent enough time writing. So I would struggle to guess at the fraction of time. The second part was
Is testing done by people?
independent people. Yes, so largely what we have adopted is that one person writes the code, and you know, comes to the point that they get something else, with or without testing. And then someone else, usually often one of these maintainers, and maybe someone else who has an interest in end-to-end pipeline data.
Last question.
Just a comment actually concerning unit tests. Basically you can set up any continuous iterations server to set up. You just commit your changes and unit tests run automatically without any intervention.
So this is one of the things where I think we could have used a lot more help and still can use a lot more help. And I think this is something to think about if you're going to do this yourself. So the first thing is to find your local friendly software engineer, if you don't already have one, and ask them how to go about some of these things. The second thing is that if you can, you know, if you have the option to get their help on some of this stuff, do, because just getting 5 or 6 people to where they were familiar enough with the version control system to where they could check stuff in and out of it was a hurdle, right? And if then someone also has to be responsible for setting up the automated unit testing once somebody checks something into that system, and so on and so forth, there's a lot of stuff which, you know, a software engineer might take them a day to set up a repository to get sort of unit tests, etc. But the astronomer, you know, doesn't even know where to start, and that's my challenge. I mean, my unit tests are, you know, I run a command that says test log, and I read the outputs and see if it makes sense. Which, you know, if you ever ran the tests for, you know, like NumPy or SciPy, you know, it just totters along and at the end says it passed all the tests. So, you know, get yourself help, and especially for some of these more complex things, it's worth trying to get help from someone who's a professional, even if only for a day or two to really get you going on how to do some of this stuff.
Okay, you go. Okay, so now we have, I'm sure we're not going to say this right, Saji Philip. Is that okay? Yeah. Yes, sir. Learning from partial information.
I'll be presenting two case studies rather than going into the theoretical aspect of learning from partial information. And in this case, I'll be mostly dealing with classification problems where whether you are using statistical method or machine learning or any other tool, you are assuming that all your classes are separable in the feature space. So it could be a plane, it could be a hypersurface, or it could be a projection to a surface. And in the first case, we are trying to classify the photometric classification of point sources from SDSs using a homogeneous set of features, which means that all the features that we use here are fixed for all the different examples, and I'll explain it later in detail. So what is assumed is that you have a set of objects for which you know the exact nature and the classes are known, and you want to find out for the remaining objects what the classes are. So in this particular case, we are studying this particular region in the color space of the SDSS colors, SDSS objects. There are about 150,000 objects confirmed with spectroscopy, the nature, and there are about 6 million unconfirmed cases in the small box with photometric information. So all the objects have known colors, which is the partial information we have, but the confirmation with spectra, and therefore the classes are unknown. So the challenge is to find out the class of those 6 million objects. Now Bayesian algorithm, for example, as we all agree, gives the best result in all these cases, because we can always define the likelihood and the prior if we can. Well, so the problem simplifies to the following. SDSS provides 5 magnitudes for each object in the U, V, R, I, Z bands, and we have constructed a dimensional color space. We have about 150,000 objects with known classes, so we can take a subset of that and use it to estimate the likelihood. The classification can be tested on the remaining data to verify that. But unfortunately, this won't work because the distribution is not smooth, and one has to build the color space to approximate the distribution. And this creates problem because computing conditional likelihood of the bin high dimensional feature space is nearly an impossible task. So these are two issues whenever Bayesian methods is used. One is the prior and the other is the conditional dependency. How can one guess the true value of the prior for each bin? And the conditional dependency of the input feature space makes the likelihood conditionally dependent on the feature vectors. And if we ignore that, null Bayesian models, we know that they ignore conditional dependence, they even on simple XOR problems. So that won't give us the desired result. Various methods have been tried for this. Principal methods, bagging, boosting, Bayesian model averaging, Bayesian model combination, etc. But we decided to stick on to boosting method because that is simpler, and you can use the gradient descent algorithm, for example, to estimate the weights, which becomes the prior for the particular model. Then we need to estimate the likelihood of the bin space. This becomes an issue because there may not be sufficient samples in each bin to estimate the likelihood when conditional dependence constraints are imposed on them. So we adopted an imposed conditional independence formula that approximates the likelihood for a conditionally dependent event. And what we mean by that is the following. The likelihood for a conditionally dependent event A is approximated as likelihood for A given B, C, D, E, F, which are the features, is approximated as some constant multiplied by the likelihood for A given B, C, A given B, D, etc. All the combinations possible. And it can be shown that this works better than the Bayesian null bias, and also it does not produce any issue with XOR or similar case. Now we went to the 6 million objects, did a classification of them, and found that what is shown on the right hand side, for example, is the 3-dimensional color space, in which you see the blue colors, they are the predicted quasars, the yellow colors are predicted galaxies, and the green are main sequence stars, which are predicted in the 6 million. But how will you know whether it is correct or not? So what we did is that we went to 30 different surveys, and all this was possible, especially because of the virtual survey which was available. And we went to look for objects in our catalog, which were also in those catalogs with spectroscopy confirmation. And as you can see here, most of them were classified with very good accuracy, more than 90%, 95% accuracy. And that we thought would be a very good result and send the paper for publication in MNRS. We got a very good referee who gave us very detailed comments and also said that this need to be verified further before it can be published. One of the suggestions he made was that we should compare our predictions with the expected quasar number counts or the quasar number density in different magnitudes. And what is shown here is those red and blue, those are the expected number density from a quasar, and what the black dots are what are just as you can missing values. But that is not an easy solution when in a situation where if you do not have the training data with all the features for computing this problem. And such a situation exists in the Deltina real-time transient survey, where we were trying to develop an annotator for predicting the loss of black holes. So the challenging problem is to generate alerts on optical transient detections, minimize false detection, customize alerts to user demands, send alarms immediately with minimum information. But the inputs we have are the nearest distance to something like to galaxy or star, distance to nearest known radio object, distance to nearest X-ray detections, magnitude in archives and similar. It produces missing value because those are long tails. So there is no way to compute the inverse probability and it makes it impossible for standard machine learning algorithms to learn and predict. But as I said earlier, we have the conditional independence which we defined earlier, which allows us to take the likelihood as the product of combined likelihoods. So whatever information that is available, estimate approximate likelihood based on whatever information is available and use it for training and testing is the method we have. And this requires dynamic learning because with a lot of missing values in the observations, each input data has partial information about the features associated with the outcome. So one has to learn as we go, use Bayes update rule to do that, and update the belief in each of the features and its effects on them. Then it is possible to add features dynamically. We want to use all available information about the detections as and when they become available. Since likelihood is computed as the product, it is also missing ratios. And we wanted to see whether we can create dreams for them. We use error bars for that, providing that information, because error bars tells us that the nature of the object remains the same even if the measurement value is perturbed within the range of that. So we can use that to produce additional data for it. And with the help of Ashish Mahabal at Caltech and the CRPS team, we were able to generate an annotator for the classification. And initially it turned out that the classifier gave very good accuracy when it was trained. And this is the accuracy we got on the, about 90% of the data was used for training. So it gave us good accuracy. We are trying to classify it with a different process. But of course, the recall is good and the false alarms are also low. But when we tried it on the recent data that is available in CRPS, we found that there are a lot of failures, as can be seen by the red numbers there. So this is a confusion matrix. So it shows that there are a lot of errors. But it is also seen that the results are better than it could be. It's saying it could be anything. Because if you look, these are the first 4 columns are the possible classes of the objects based on the Bayesian probability. The highest Bayesian probability is given in the first column, second highest is given in the second column. And these are all failed cases. You can see that in most of the cases, the second highest Bayesian probability is for the correct class, actual class, which are shown in blue color here. And in some cases, of course, you have, this is a random pick from the data set. So you find that in many cases, is giving an answer, say it's better than it would be there. So this work is still in progress. We have
50 or 60% missing data.
Yeah. See, whenever there is a missing data, that is not used for computing the likelihood.
Right.
When only those information that is available is used for computing the likelihood. Once you estimate the approximate likelihood, you use the Bayesian rule to find out the problem.
Right.
So it does not in fact affect how many, more than that, it favors if you have more information available.
Sure.
Rather than, if you don't have any information, then whatever you get is.
Right.
What was the factual object? How many objects are missing?
Missing data.
Yeah,
Almost all of them, because you are using all the available information for those, and many of them do not fall into any of the subjects. That's why we cannot compute the inverse problem.
More questions? Okay, thank you very much. So it's coffee time now. There's coffees out there. If we can be back here at 10:50, let's do that. Thank you.
But when I first so I don't know what it would be. I'll ask him. He has the magic name or something. I just don't get it.
I prefer having the USB sticks, but if you have video,
Are you running this?
So you want to test yours first, and then I'll go last, and then mine's set up and goes up a mess.
So I can try it.
no, I haven't.
Okay, I will try that. I tried 0.0, that didn't work. So. Yeah, mine doesn't. It says undefined variable when I echo it after I log in. So.
Let me just, 1 second.
I get 18 as well. Local has 18. Oh, okay. Because
But it's still, but then it generates the X11 on my side. So if I delete the X11 on my side. Oh, okay.
No, yeah. Okay.
So that's the trick with Max.
Pardon me?
You have to connect these two first.
Oh, okay, so it should.
That's one of the big things with Mac. I learned from the history. So, Chris,
Okay.
you'll be okay to test this? Alright.
Now, if for some reason it still launches, then my script goes in and it launches X11 off of Redux. It's a Python script that calls matplotlib to create a PNG file. And so I guess when it calls matplotlib, it needs to call an X11 session and automatically export it to the web.
No, not to my knowledge anyway.
Pardon me? Well, so as soon as I exit out of the screen session and I disconnect from Surface, it won't disconnect because I still have an X11 terminal open. So when I kill that X11 terminal, then my script dies because it can't find the X11. So, yeah, because I have to create a ridiculous number of images, postage stamps. Like what I've been doing is I'm just running it, hoping that my internet doesn't crash, and if it crashes, I have to relaunch it, right? So, which is useless and pointless, really. So, okay. Well, now that I know what the cause is, because before I didn't know what the cause was.
It would still be good to have your maybe look at some of the
Well, that's what you can see what he says. He seems very puzzled by this too.
On the web, yeah, I can make it myself.
Yeah, well, now because I like to look at one.
Yeah, it is. It's a Python.
Yeah, I said that.
Yeah. Well, it can attach if it wants, but it has to attach to the correct one. It needs to attach to the one on the machine that's running it. And then if I lose my internet connection, it's okay because it's still running that. Okay. Oh, that's so frustrating.
If you can.
Yeah.
Tutorated means you've got, so it's one profile and one user. That's right, yeah.
No, I think it's two things. I had it done.
Don't worry about it.
problem
It's just an internal transfer. We'll just drive slowly. Nobody can look. So after Thursday, so Thursday morning it's really up to you. After lunch it's almost full. Okay, good.
We're fine.
I think we're there. I don't touch it. Can't touch it anymore. We have to be yeah. Yeah. So invited speakers have got 30-minute slots. 30 minutes plus 10 questions. And contributing talks are 20 total, which is 15 minutes.
I mean, we should do that every night.
The main issue is, yes, it's our computers, but the main issue is all the admin stuff. So you can't sort out it, get all the things around. Oh, they come to rescue me. Maybe I shouldn't have known.
Just testing for wild states, things like that. The thing is, the code set, you have that. That's it. And then when you get to lit, things at the end of the day, when everyone's doing these solutions, all the users that we have and all the users that we so we have rules every month. Yeah, there's lots of things out there. I mean, this is good.
know you don't manage it, but you can at a certain point remove everything
Yeah, we've been to
Hear the sound of the big size of relief there. So they wonder, so that's actually
Okay, hi everyone. So before we get started in this session, I just wanted to say something about the discussion that's coming up at the end of the session. So I thought, following on from the discussion yesterday and thinking about what are the useful things that we can do when we have a really diverse group of people like this together, the question I want to ask is, what is your single most pressing problem in the astroinformatics space with the projects you're working on right now? So not thinking about what might be a problem for you in 15 years' time, but what's your problem in your project that is sort of stopping you or a challenge right now? And I thought this would be useful to discuss, because if everyone shares what their issues are, there might be other people right here in this meeting this week that can help talk about, can help you with your issues. So not everyone gets a chance to give a talk, but everyone can at least get some discussion about their project through this. So that's something to think about at the end of this session. Now this session is going to be very interesting, all about visualization, so I'm very excited to see the cool things that people are doing. And our first speaker is Chris Flute from Swinburne, who's going to talk about the big challenges of visualization.
Great, thank you, Tara. There's actually two ways you can read this title, and you can choose as you go along and change between them. One of them is Big Data Visualization and Analysis Challenges, and the other is Big Data Visualization. I need to thank my key collaborators here. My main partner in crime is David Barnes, who'll be visiting on Thursday to talk about some of the work that he's now doing in biomedical visualization.
Hassan, my PhD student who's done a lot of the hard work behind the scenes in getting some of these things to work, and Bernard Mead, my current master's student. I also want to thank Ray Norris and the organising committee for inviting me. Ray wrote a paper on the future of visualization for the ADAS conference proceedings in the early 1990s, and it's been quite I think sort of a template for me in how I'd like to see visualization advanced, and I'm also a little bit disturbed that over 20 years it actually hasn't really advanced as far as we might have hoped it has. So here's basically what I want to talk to you about today, is that the big data era presents a serious challenge to traditional desktop-based visualization and analysis. And I need to spend a little bit of time unpacking this statement for you so that I can at least tell you what I think each of these terms mean and see if you agree with them. But basically, big data is when your accumulated data exceeds your ability to capture it on a local resource or some local storage facility, and it gets increasingly hard to manipulate or do anything with it. Now, big data appears in many different guises, and we've heard about some of them this week, and we'll continue to hear about more of them. There is the big data problem when you have many individual files, but each of those files is actually quite small. And I like to think of that as the big small data problem. And as far as a desktop traditional approach, it's probably okay. As long as the data is managed effectively behind the scenes, you can keep doing what you're doing on your desktop without too many difficulties. Then you move on to dealing with maybe one very large file, the small big data problem. And you have to ask yourself, what am I saying it's big compared to? Is it big compared to the system memory of my machine? It's in one place. So next I need to tell you what I think visualization is. And visualization, I think, is crucial to this magical process called knowledge discovery. And here's how it works. It's really quite simple. Data goes in, you look at it, and science comes out the other side. And that science is, by being reinforcing and looking again and again, we discover more and more knowledge, we do more and more science, and ultimately we're going to publish, present, and hopefully use that for some form of education to do. And there are different ways you can think about three-dimensional visualization. Qualitative is absolutely the easiest version of all, and to just show you how easy I think it is now, we can put an interactive volume rendering of an H1 dataset into a PDF file, and I think that shows you how simple it is now. You don't need any specialized hardware. This is quite a simple way now for us to share another data set or compare it with a model. In this case, we have some 21 centimetre data of the Ursa Major galaxy cluster, and it's being volume rendered in this lovely blue-green colours that you can see there. The green is the interesting stuff, and the white boxes are from the Duchamp source finder from Matthew Whiting's work, and you can see the Duchamp catalogue overlaid within the data set. So I'm now making a comparison between an automated technique, and I'm still looking at it to see, did it do a good job? And once I'm happy that it's doing a good job, then I'll probably have more confidence to set it up in an automated mode. But the hardest part still is quantitative visualization. And this is probably the reason why three-dimensional techniques perhaps haven't taken off as much in the last 20 years as we would hope that they would. We might take our data set now and want to start asking questions of it. We want to ask, what's the median flux in some particular region? We want to work out a maximum or a minimum range. And a lot of that has to do with how we select parts of our data set. So this is where the traditional desktop is causing us a problem. Because this is our traditional desktop. It's a monitor and it's a mouse. And the mouse is a fantastic two-dimensional device, and the monitor is a fantastic two-dimensional display, and they don't quite work as well as we would like when we want to explore three-dimensional data sets. Well, alternatives to the 2D mouse are quite well known, and again, it's been well over 20 years that some of these devices This is NASA's vision from the 80s of how we would all be sitting exploring our data. It's interesting, this sort of cycle of technology. The Oculus Rift is one of the big sort of exciting new products of the last 12 months, because it's about a couple of $100 virtual reality headset that you can buy. Things like the space ball, various wands and other sorts of tracking devices for manipulating and exploring three-dimensional data sets. They work, but they're not always intuitive to use. They're expensive, and they're not really practical for our desktop. Well, in the last 12 months as well, another product has appeared, which is perhaps not the best solution, but it's showing us something very interesting about the way we might interact with our desktop. So let's see if we can get this to work. Okay, so the leap, I'm just going to put my hands in, and what's happening in real time here is it's detecting where my hands are. So it's saying I've got two hands. It's actually very good at detecting my watch, I discovered. So I learned fairly on that you have to modify how you actually addressed when you're using the leap, rather than having to write extra code to eliminate additional features that are things there. It's also very good at detecting my head. So there's our first go. It's quite a simple API to use with. This is probably an hour or two of getting to understand the API. So we're going to that point. So create your own virtual musical instrument or whatever else you happen to want to do. Now, there's a couple of different ways that you can use a device like this, and a lot of the early online games and things that are being shown are about navigation. And I actually think it's quite a silly way to use a device like this, because I don't want to sit there trying to point in and out necessarily to navigate. This is, again, quite a bad, it's more about my ability to get my hand in the right spot than anything else. I don't think that's a very good way to sit at my desk for an hour trying to hold my hand to do that, when I can do that quite efficiently with a scroll wheel on my mouse or some other device. So I'm less excited about this from a navigation perspective. But what does interest me now is the ability to do quantitative visualization. So I've got two windows here. The one on the left is showing you the space above the leap. It's an inverted pyramid that extends to about, you can see when my hand disappears, or somewhere around there, depends on the lighting conditions. And I've set up two regions in here. One is my data region, and one is my menu region. And on this side, I have the actual data that I'm interested in. So I'm mapping from coordinates of leap space into my actual physical data space. And so now I'm going to put my finger in, and I can move this around, and I can report to you a particular data value within that cube. So I now have a true three-dimensional cursor. Well, again, maybe I could do that with a 2D mouse, but what I can't easily do with a 2D mouse, and this is where my manipulation skills will really be tested, I've just changed mode, and now I have a selection. I'm going to move my sphere around, and the distance between my fingers is telling me the size of the region. So as a prototype now, this device for $80 is gives us a hint of how we might change the way at our desktop that we manipulate data. And I think it's an interesting step towards solving the issue of quantitative visualization. Okay, that demonstration worked a lot better than I hoped it might. So given the big data era and traditional desktop techniques and visualization, I've deliberately not said anything about analysis just yet. I'm going to come back to that, because visualization and analysis are actually possibly two separate things. This is the question I'm interested in then, is how can we ensure that interactive, real-time visualization and analysis remain viable components of knowledge discovery in the big data era? Because visualization plays a role, but it's not the only thing that we want to do. So here's a case study there. This was the particular area of interest, and I don't need to say very much at all about this, because Bertle's going to be talking in much more detail about H1 surveys. But the Wallaby project is designed at studying the redshift of 21 centimetre from extragalactic sources. As originally proposed, would cover 75% of the sky, looking back about 3 years and finding something like 500,000 new galaxies. If there's anyone in the room who's not familiar with spectral data cubes, what we essentially have is our two sky coordinates and a frequency which is a proxy for the line of sight velocity through the dot issue that we're thinking about, and to H1 sources that their data set, or about 48 times the entire bus data volume being volume rendered at 7 frames. Very fortunate to have this. Australia's first fully indoor national astronomy facility, G-STAR, which is the GPU supercomputer. ARM's solution worked. We have our thin client, so essentially your astronomer sitting at 3 gigabytes. We had to use 96 GPUs to do this. So this is obviously not, it's actually just as important, right? And we asked them to find a
as people adopt the technology, how spectra will be a challenge. So I didn't see any numbers.
Yeah, okay, so to load that into the memory of the 96 before a cube goes into the archive. That was the most critical place to see the whole data set, and then in the future you're probably going to only ever look at small pieces of that.
Okay, Matthew.
That did a great job, so it's described as a set of from the disk to produce, and the other really nice feature to it, let's say almost any HP. In the last generation of this simulation, you are working with like 100 billion particles and your code on a supercomputer and hope that everything will be fine. You need instead.
And people use different colors to color in the H1, so we're very interesting to mention any clouds, the stars, and the ionized.
Ready? Not that they can't, put their hand up as well, but I particularly want people who maybe don't know everyone to think about a problem that you're having with a project you're working on and just say what it is, and that way people can come up to you later and say, hey, I know how to do that, that's trivial for me, or hey, that's a really difficult problem and our group is working on that. Okay, so that was the aim of this session. I don't know if anyone is going to be brave enough to start. Yes, okay.
So this is not a problem you can solve.
Okay. Can you start by introducing yourself to the people who don't know you?
I am from media and I work on data mining in massive data sets. And I think that the worst problem I could have is facing right now is how to move in an effective way the programs to the data. Because the size of data becomes so big and so large that you cannot transfer.
By very specific theoretical problems, how do you start?
Seems effective. CSIRO is what it's trying to say.
I'll look into it. And the person will respond to it.